thank you for being on the call tonight. I'm not competing with an inauguration or an insurrection, so I suppose that's a positive thing. But definitely want to talk tonight about some of the research that I'm doing at NIU Northern Illinois in DeKalb, and really my perspective on tornado history, where we are now in terms of our ability to predict, forecast, and then looking ahead to future, and with various aspects of what I think future forecast might look like, but also the potential changes in the landscape of severe convective storms due to an expanding urban footprint and climate change. So again, thanks for the invitation and thanks for tuning in tonight. Um, I hope this is informal. You're not going to hurt my feelings if you're having a beer and relaxing and trying to, just get away from the work day, if you will, and just enjoy some weather nerdiness. So I call this severe storms, past, present, and future, and we're going to cover a lot in about an hour. But I start all my talks just sort of introducing myself as a human. Yeah, I spend a lot of time behind a terminal every day, and I do a lot of coding in my job, especially in regards to research. Um, but I like to think I have a life outside of academia. I'm a craft beer snob. I started actually in academia working at the College of DuPage. And so if you've ever used weather.cod.edu and looked at their model graphics at their satellite page, I had a heavy hand in developing that and actually still continue to support their models page. I get out in the field every year, generally anywhere between 10,000 and 20,000 miles chasing. When I was leading trips for the College of DuPage, um, I was doing it upwards of 20,000 miles a year. And I don't chase that much anymore. And thankfully, the last 2 years have been very dull for tornadoes in the plains. And I haven't had to travel too much, but I do enjoy getting out in the field because every time I'm out in the field, I feel like I learned something. Um, I'm a purple martin landlord. For those of you who know what purple martins are, they're fantastic birds that migrate every year from South America up into the central plains and even up into central Canada, where they over summer, they have their young and then they fly back to South America. And in fact, they're very loyal birds and they'll continue to come back to the same roost every year, which is pretty fascinating. So here I am showing off the director of the National Weather Service, Louis Uccellini, and at the time, the MIC in Chicago, Ed Fenelon. So we were doing a mobile weather discussion. And that's a younger, perhaps more handsome picture of me, I'm not sure. But I am a weather nerd, as sort of Jared alluded to. I think many of you on this call probably are. And I have a stipulation, maybe an inkling that if you're listening to a weather talk about tornadoes at 7:30 on a Thursday evening, you're probably a weather nerd too. But here's my annual Halloween costume, and this year I actually added a dry line to my right, in this picture, my left leg. So that's my extra tropical cyclone Halloween costume. So I got interested in atmospheric science actually I was on a path for engineering in high school, and it was okay. I liked, I wouldn't say I was good at math. I liked science. Um, and I just kind of thought that engineering was sort of the way I wanted to go. I like to tinker with things, build things, and then terrible Tuesday in the Illinois Valley happened. This was a very interesting event. If you're familiar with this particular day, it was a rapidly northward retreating warm front, and there was a narrow window of sunshine south of the warm front that allowed low top supercells to form in sort of a really enhanced region of low level storm relative helicity. And as is the case, oftentimes in these Midwestern warm fronts, you get these really grungy looking wedge style tornadoes. And this one just happened to hit my high school in Granville, Illinois, as you can see here in the lower left, and actually crossed the Illinois River in two places before hitting the town of Utica and unfortunately killing 8 people that took shelter in what they thought at the time was the sturdiest building in Utica, the Milestone Tap. So this inset here is from north central Illinois. If you're not familiar with this area, it's right where the Illinois River makes a kink and begins to bend southward to flow towards the Mississippi. So after this event, obviously the physical, if you've seen tornado damage, the physical scar that tornado damage leaves behind, but also I was very interested in the mental aspect and the mental scar that was left behind on people. For those of you, especially in the Weather Service, that have been out on damage surveys, going in and talking with people the day of is completely different than going back a couple of days later and talking to them. The initial day is, shock, no idea what happened. And oftentimes when I come back a few days later, it's almost like comic relief. They realize, their community has coalesced together to clean up. They begin to sort of make a joke out of this, and they always use that defining moment of, what happened my life before the tornado and what happened after, right? Things just aren't the same after these events occur. A lot of my research now is really motivated by the increase in billion-dollar severe weather losses, which are the green bars on this chart back to 1980. You can see in recent decades, it's pretty uncommon not to have a billion-dollar event. And in fact, we're averaging about 10 $1 billion loss events every year now. Part of this, as I'll show later, is just the expanding footprint of cities and developed land. But there also, we think, is a shift in the climate regime, and specifically in some locations where these events are happening, that are making us humans just more vulnerable to these types of losses. And so obviously this is, something that is become really a national priority. If you're familiar with any of my work, it's probably because of the media. I do a lot of media outreach. I like to be a science communicator. I sometimes am good at it. But the first question I always get from reporters, whether it's the Associated Press or local, campus newspapers, is, did climate change cause this event? And I think most of you on this call understand that that's not the case. These questions are usually framed in an a priori sense, trying to address a specific agenda, right? And so I always ask, what are you blaming, and why are you framing it as a cause versus a contributor? It's easy to point the finger and play the blame game on a specific event, and we've become really lazy as a culture in doing this in many different aspects, not just climate. But of course, we know that it's not that simple. Climate change is, of course, playing a role in the changing the probability, distribution of these events occurring. I like to think of it more as we're changing. We have a set of die, and we're changing. One of them has an extra 6 on it. That doesn't mean we're going to roll, box cars every time, but it certainly changes the probability that over the course of time that we're going to roll more box cars. And so there are some studies that are beginning to come out that are in their infancy. That is what I'm very interested in, which is called attribution science, which are these very preliminary research, usually modeling studies, that are trying to attribute something like a Hurricane Katrina or a Hurricane Wilma or a Midwestern United States derecho of August of last year to a specific either climate factor or to anthropogenic climate change itself. And I will just caution by saying that when you see this stuff in the media, it's usually sensationalism. My work at the University of Georgia was primarily on this. It was severe convective storms and climate change. I really wanted to understand the distribution of tornadoes as a function of how they were changing with respect to time, and all of these little changes and blips that you see in the time series, if those in any way related to tornado frequency across the United States. And then April 2011 happened. And that, to me, really shifted my motivation from looking at climate change to looking at climate variability. And just to show you here, and as an example, the color-filled contours that you see in the background map here are the frequency of the number of hours in April 2011 that we had a significant tornado parameter value greater than 1. And of course, just very subjectively, I have the tornado LSRs here, the local storm reports. You can just visually see, right? Those are highly correlated, that tornado environments produce tornadoes, no surprise. Well, this caused some great discussion all the way up to the White House. In fact, this was during Obama's administration, and there was actually a white paper that was released that said very clearly that we needed to advance A, lead time for tornadoes, and B, investigate new forecasting methods to predict outbreaks further in advance. Pretty open-ended. But we took that in the research community to mean we need to start investigating why this would happen versus an April 2016, for example, where I have the same thing, the frequency of the number of hours of STP in the color fill in the background and the LSRs. And so very clearly, right, an April is not always an April. Not all Aprils are created equal. Now, April 2011 spawned something very, very important in the Southeastern United States due to a senator and some earmarked funds in Alabama, Vortex Southeast, right? We started getting funding to investigate the societal impacts, which are really the most important in the Southeast, because that's where we have a vulnerable population living in weak frame housing stock. You know, Walker Ashley, Stephen Strader, and others have shown that this is the most vulnerable area probably in the world to tornado fatalities. Well, go ahead. Here's the first year of the field project, right? Like any good field project, you're missing observations in your domain. This was the first year of Vortex Southeast, and of course, there wasn't a lot of activity. And of course, that's fascinating to me as somebody who's looking at climate variability, because what made April 2011 so prolific, and it made something like April 2016 so quiet. Okay, so that's one of the things I want to touch on tonight, especially as we talk about the future of severe convective storm forecasting. My two sort of leading questions right now in my research are, number one, are there modes of climate variability? And I'll talk about what leading modes actually means later, how they affect severe convective storms. And when I say severe convective storms, I'm referring to the US definition. So large hail greater than 1 inch in diameter, 50-knot convective wind gusts, and tornadoes. And also, I'm still very interested in this climate change angle. And if climate change hasn't played a role to this point, what is the theoretical for potential impact on climate change? I mentioned that I spend a lot of time every day behind a computer terminal, and I am I would consider myself a dangerous coder, but I'm not certainly a computer scientist by any means. I dabble in everything from, Linux to running high performance computing clusters on the world's fastest computers. I use a lot of statistics, modeling, things like WRF, MPAS, and the new version of the global model from NOAA, which is their FV3 model. And really what has, I think, changed my research in the last 2 years and is going to continue to change our field as a whole is artificial intelligence and deep learning, machine learning. The ability for, as humans, one of the fascinating things that I see with humans, especially good forecasters, they have this intangible ability to look at a map, usually a map that's, pseudo 2 dimensions. So example, a 500 millibar height map, even though we know the 500 millibar height surface is, a 3-dimensional quantity, and we're looking at it on a 2D map. They have this innate ability to visualize things in a 4-dimensional way, play out conceptual models in their brain, and do a lot of pattern matching, right? It's very well documented in the literature that meteorologists are very, very good at rotating conceptual models of things in their heads. Like we're good at pattern recognition. Thankfully, so are computers, and machine learning, and especially neural networks and deep learning are really changing our field in the way that we're going to be able to do this, these sorts of ask and answer these sorts of research questions in the future. All right, before I launch into the good stuff, I just want to mention that you can put stuff in the chat bar, although I'm not really paying too much attention to the chat. We will certainly answer those later. And if you do have a burning question that you feel like you need to interrupt me and jump in, please feel free to do so. But I want to, just for a second here, I want to back up and make sure that my presentation, that it's going to share audio, because I do have an audio here that I just want to make sure is going to work. So let's see here. I need to share computer sound. I forgot to do that. Okay. So let me pop that back up over here and we should be good. Okay. Are we back? Thumbs up?
Yep.
Okay, cool. So do a really quick overview of history, sort of how we got here in relation to severe convective storms. And again, like I said, talk a little bit about what's going on now in the latest and greatest of SCS research, and then launching into the future. So I'm going to start by showing you just a very quick 30-second video.
The most devastating series of tornadoes in many decades rips through 6 Midwestern states. In the wake of the twisters, there are nearly 250 people dead, with damages mounting to the hundreds of millions of dollars. Iowa, Wisconsin, Arkansas, Indiana, Illinois, and Michigan were all hard hit by the deadly tornadoes as they slashed across the heart of the Midwest.
This was the aftermath of Palm Sunday, 1965. Not
Palm Sunday, 1965. How many people remember that event? I see some hands waving in the crowd. Yeah. Remarkable event. If you look at it through in history, we've actually done some modeling on this particular event, going back and using the 20th century reanalysis and some of the updraft helicity tracks that were created. If you were a forecaster on that day and you had access to CAMs, convective allowing models, right, the HER, the rapid refresh, you would have definitely been sounding the alarm bells from what we can tell on our reforecast runs with WRF. But a remarkable event. And I show you that video just to show you that to talk a little bit about the record, okay, of tornadoes. Now, this goes all the way back to some of the work that Tom Grzoulis has done looking at significant tornadoes in the late 1800s, spanning all the way to present. Our modern record of tornado reporting starts in about 1954. The early 1950s are a little sketch. We don't really like to use those data points unless we absolutely have to. But if you start on and around 1954, I have a chart here looking at, let's just take significant tornadoes, for example. You'll notice that they've actually been very consistent with respect to time. And in fact, if anything, in the last couple of decades, the number of significant tornadoes has slightly decreased. If you include hail and wind in this discussion, then you see this giant, right, exponential increase in the number of reports with respect to time. Clearly non-meteorological, but something that a lot of people like to blame climate change on. I mean, this is very clearly a function of lots of things: Doppler radar detection, storm chasers, the advent of Skywarn, right? Cell phones. I mean, look, in 1950, it was pretty easy for an EF0 in Kansas, right, to go unnoticed. Now, if it hit a farm or caused a fatality, it was definitely going to get recorded. But if it was just a wide open, land spout in a field, it wasn't getting reported. Now, right, this picture on the left, we have 100 chasers on every single storm, every single year in May in the plains, and even little swirly EF0 bird farts get entered into the record. So we do have this inflation happening in severe weather reports with respect to time. And it's important to understand that there needs to be normalization, right, that's accounted for when we begin to look at temporal records of reports with respect to time. I actually don't like to look at reports. I think they're fine. I mean, they document some of the bigger events. But for those of you who understand the Fujita scale, you know that it's a damage-based scale and there's inherent subjectivity when A, you're rating a tornado, or B, you have to have assets for the tornado to hit. And so, tornadoes in the southeastern United States are often rated higher as we have higher population densities and more structures for these tornadoes to hit. So I like to instead look at what I call the ingredients-based approach. So I'm much more fascinated in things like tornado watches than, the actual tornadoes themselves from a scientific point of view, because this is something, the ingredients are something that we can look at in a much more objective manner. We know that if you want severe storms, you have to have SLIM, right? You have to have shear of the wind, vertical wind, you have to have lift, you have to have instability, you have to have moisture. If you just have lift, instability, and moisture, you can get convection, but it's not going to be organized convection. Right? You need that shear component for the organization. So I like to do is take these ingredients that we know are going to cause, potentially cause tornadoes. In other words, we're looking at sort of favorable environments. Think of it again as a tornado watch situation. And we can use reanalyses data to then map out where and when these events are most likely to occur. So we're not like explicitly looking at tornadoes, but we're looking at their background convective environment. The most seminal paper to look at this was published in 2003 by Harold Brooks, his student at the time, Jamie Lee, and Jeff Craven. I still think this is one of my favorite papers going back in history, and they did something that was pretty simple. They plotted vertical wind shear on the y-axis against instability on the x-axis. And if you do that and begin to stratify these events between sort of run-of-the-mill severe weather and then something we classify as significant severe weather, 2-inch hail, EF2 or greater tornado, right? 65 knot greater. So you're getting to the upper echelon of these reports. What you see is that there's a pretty clear parameter space for these big, big boy, big girl events to happen. And they happen under regimes of significant vertical wind shear and significant buoyancy. So you can take that, right? Take the vertical wind shear, take the buoyancy, and begin to plot it globally. So here's my sort of best guess analyses of globally based on the parameter space that we know is favorable in places like the United States and Europe, map it globally and kind of show where are some of the global hotspots for tornado activity. Certainly all of us here are, if you like tornadoes, you're really happy that you live in North America. The Central Great Plains, of course, given our geography and our raised topography to the west, create the steep lapse rates and the cape that we need for that buoyancy term. But you'll notice, right, we don't have tornado events in the tropics, or tornado, I shouldn't say events. We don't have tornado environments in the tropics. We don't have them generally north and south of 60 degrees. And these are mid-latitude phenomena. I mean, there's no question about that. But some areas that you may not have thought about before actually do pop out globally. We see sort of global hotspots in southern Brazil and Argentina, portions of South Africa, and actually Southeast Asia. Bangladesh is one of the tornado hotspots of the world. And you see a relative maximum actually in Eastern Australia as well. So it's kind of cool, we can use this parameter space knowing that we don't have reports from all over the globe. Not everybody is keeping a tornado climatology like the Storm Prediction Center is, but we can still try to make assumptions or guesses as to the relative frequency of these events, knowing that the physics is not going to change from one location to the next, right? The frequency certainly changes, but the physics are the physics of the physics, whether that's the Southeastern United States, the Great Plains, Australia, South America, wherever. We're confident that the physics, the laws of thermodynamics are going to be the same from one continent to the next. My master's thesis actually focused in on looking at the United States in particular in a much higher resolution than the map that I just provided there. So this was basically really focused in on, can we create an objective tornado alley? For a lack of a better term. I mean, a lot of people throw around Dixie Alley, a lot of people throw around Tornado Alley. I hate the term alley. We can talk about why I hate it later. But this to me is what I would call the true right-moving supercell climatology. And you can see it actually extends up into central Minnesota. I mean, there's no surprise there. Southern Minnesota, as you guys are aware, this is sort of, you can actually see where you transition into much more of a wooded landscape in eastern and northeastern Minnesota. But southern Minnesota, of course, is home to and has a long history of significant tornado events. And you can see that red color. I don't think a lot of people realize this, but look at some of these frequencies in southern Minnesota. I mean, we're talking reds and purples. Those are of the same frequency, folks, as the eastern Texas Panhandle. And so there's some maybe perception that that's not the case, but it is if you look at the data over a long period of time. And again, these are kind of looking at climatologies of you could imagine these as a frequency of tornado climatology in terms of number of days per year. The Southern Plains, by the way, while it does have a much higher frequency than any other area, is very seasonal in nature. It comes and goes, it shuts off really quickly. I mean, there's a reason storm chasers go to Texas and Oklahoma for basically 2 weeks in May, because the seasonal cycle there is so strongly correlated to the dry line. Whereas somewhere in like the Midwestern United States or Eastern Nebraska or Iowa, there's a lot of variability that our severe weather seasons have. I think of Illinois, our peak tornado climatology in Illinois is actually the second week in June, but we've had documented tornadoes in January, February, all 12 months. So it's not as clear cut when, there's certainly a perception maybe that the Southern Plains is the world's hotspot, but I caution you to kind of think outside that box a little bit more, that these are just not, central and Southern Great Plains phenomena. Of course, in those corridors, we've had some pretty significant events. I think of, one of the many Moore, Oklahoma tornadoes. Here's a picture of the Moore, Oklahoma F5 of May 20, 2013. I I don't know how many of you have seen this video, but I have to play it. It's my favorite tornado video of all time. It's from Columbus, Nebraska. This was a major instability day along a warm front. I kind of think of it almost as a Pilger type of day. If you guys remember the Pilger twin tornadoes of eastern Nebraska, that reminds me of this particular setup in late June of '98. But I do want to show you this video really quickly because it's one of the most classic tornado videos in history.
Shit. Susan, get my pants.
If you had difficulty hearing that, this gentleman is out on his porch staring down a wedge tornado that's not moving left and it's not moving right. It's just getting bigger, right? So it's coming right at you. And he yells to his wife to please get him his pants. Says, Susan, get my pants. So he's watching this large wedge tornado approach his farm in his underwear. It's one of the most classic tornado videos, I think, of all time. And many of us storm chasers look to that video for comedy quite often. Outside of this alley, we've had significant events. I just played the video from Ed Hurley looking at the April, the Palm Sunday 1965 event, which was the twin tornado photograph prior to the Pilger outbreak in eastern Nebraska, the Pilger-Stratton tornadoes. And so these are twin EF4 tornadoes. This famous picture from the Midway mobile home park in northwestern Indiana. But still, this is one of the most famous tornado photographs of all time in the NOAA library. And it's still one of those events that I look back to as, what is the atmosphere really capable of? And when you start to look at those extreme events, you see that there actually are some pretty remarkable things that we have not seen in the modern era in the last 30 years. I'm going to skip this slide. It's just a little bit about my background research, but I do want to show you this particular plot because this is just documenting, showing you the correlation between tornado counts in blue line here and the accumulated significant tornado parameter across the United States. And so what I'm basically trying to show you in this graph is that favorable environments for tornadoes strongly correlate to number of tornadoes. Woohoo, big surprise. Actually, it is a really big deal because if we can work with the environments in a much more manageable and objective way and not touch the reports that we know have such a significant bias because they're made by humans, they go through a reporting process that's not, precise. It's a lot easier to move away from reports and focus on these environments that we know are strongly correlated at the end of the day to the number of tornadoes that we're going to see. And so this is the paper that probably my paper, at least to date, that has got the most media attention, that looked at not only tornadoes, but also their environments and how they were changing spatially. And so you may have heard, this has been a few years now, tornadoes are shifting away from the Great Plains and they're coming to get you if you live in the Midwest, or tornadoes, if you're a Trump supporter in the Sun Belt, right, they're coming to get you. There's so many, I never read the comments on an article that talks about your research. I guess that it goes without saying, never read the comments, but this particular paper did a look at examine, right, what are the trends in severe weather frequency across the plains. And we did this with hail. I actually published another paper a couple years later looking at just hail environments. But tornado environments across the Great Plains, that doesn't mean the Great Plains are not still number one. They're still number one in terms of frequency, but their trend is down over the last 50 years. And actually it's strongly down in portions of the South Central Plains. And at the same time has been increasing pretty rapidly in portions of the upper Midwest, Southeast, even portions of the Northeast. A lot of these increases are statistically significant. And they're important because when you start thinking about the trend in frequency, once you get to about this line, right in here, right, you get into the Arklatex and you begin getting east of the Mississippi River, this is where we know our documented vulnerability to tornadoes begins to increase. If you look at the mobile home density, per county in the Southeast, it's much higher than anywhere else outside of Native American reservations in the country. And so we have some issues still that we're still struggling with, that we have this increasing potential frequency, and we know there's a significant vulnerability in some of these areas too. So of course this made the media rounds, and I was becoming famous for telling people that Tornado Alley was shifting, even though, again, I hate that word, and I even specifically told the editors on the news articles not to use Tornado Alley. Of course, they don't care what I say, but I think the message here is that we don't want to tell people that Tornado Alley is not where they think it is, but Tornado Alley is certainly not a good representation for a conceptual model of where most people think it is. If I give you a pencil and ask you to sit down on a map and draw Tornado Alley, hardly anybody puts Indiana in that value. Hardly anybody would put Mississippi in. Hardly anybody would put Alabama in. And yet, this is where we see strong tornadoes. If you look at the significant tornado climatology, it's actually much more biased towards the eastern and southeastern United States. So we have some education, I think, and we need to change, maybe have a paradigm shift in regards to what we're teaching when it comes to this media-derived concept of Tornado Alley. This is probably my most humbling moment as a researcher. Jeffrey Katerba from the Omaha World Herald made a cartoon that was on the front page of the Omaha World Herald back in 2018. And he drew this funny cartoon saying that it's a twister family here. And you can see the paper on the ground says tornadoes shift to the east. And he's saying, I don't care what other people are doing, we're staying put. And I have that framed actually in my office in here, and I look at it with comedic relief. But it's kind of cool, I think, when you see your research being not only used in mainstream, but mostly to bring awareness to a problem that we've been seeing over the last decade, which is a significant bias in the number of fatalities we see every year due to tornadoes happening in the east and southeast United States. So if I had to summarize what the past has told us about tornadoes, I had to put this in here. People apparently in Nebraska film tornadoes without wearing pants. I just had to throw that in there. I want to be clear that there's really not a change at all in the annual frequency of severe convective storms. And in fact, if you really had to pin me against a wall and say what's changing right now, it's a spatial shift and actually a slight decrease in things like significant tornadoes over the last decade. So that doesn't really fit the narrative, right, of increasing tornadoes with climate change. One thing that is documented and something that I'm fascinated in is there's a pretty solid evidence for increasing variability from year to year. In other words, we have some years that are prolific tornado years, 2011, 2003, 2008. And then we have the 2019s, which was really quiet outside of late May, 2020, which was abysmal. If you're a tornado climatologist, there really wasn't, a lot of significant events to talk about. This we think is related to atmospheric blocking and changes in the Rossby waves and the jet stream structures that set up these convective environments. I'm really focused right now on looking at a lot of that internal climate variability and how it can set up to create these modes that are either really favorable for tornado activity or really not at all. I will say, from an insurance perspective and a reinsurance perspective, and people that are underwriting this sort of risk, they are very keenly aware of these changes, and they are reflected in things like insurance premiums or catastrophe bonds when it comes to underwriting the risk of severe convective storms. Severe convective storms are not like hurricanes to the insurance industry. They're not like hurricanes to the reinsurance industry. Severe convective storms, they deal with severe convective storms as paper cuts. They're paper cuts. But when you have 10 paper cuts in a year, 10 of these billion-dollar disasters, all of a sudden you have a bleeding hand and you're trying, right? You need to go to the ER. And the insurance companies right now are struggling with what to do with severe convective storms because of the frequency at which things like hail are making impacts on their portfolios. And we can talk about that a little bit later too. I'm pretty fascinated. I do consult. I didn't mention this earlier, but I am a certified consulting meteorologist through the AMS, and I do consult with insurance companies and other private entities that look at assessing and underwriting risk from severe convective storms. So this part's going to go really fast. Most of you are pretty familiar with how we forecast for severe weather in the United States. All official forecasts are issued. All official government forecasts are issued by the Storm Prediction Center in Norman, Oklahoma. They have a really nice structure. I'm obviously biased, but I think they're one of the better branches within NOAA. Their operational national center has really been a trailblazer in terms of bringing products to users, transparent in publishing research and moving science in a positive direction to impact people. So you're probably familiar with their convective outlooks. Of course, they are the ones that issue watches and warnings, and then the local WFOs take it from there. But there's been significant advances, right, in tornado forecasts in the last few years. We now have, individual hazards for day 2. SPC starts now, they now forecast out as many as 8 days in advance for these particular events. And, massive hats off to not only the folks at the Storm Prediction Center, but also the local WFOs that they collaborate with, because, the National Weather Service, in my opinion, is a really unsung success in many circles of the federal government that doesn't get the credit it deserves. And quite frankly, is, again, in my opinion, I think a no-brainer in terms of an investment. When you look at your tax dollars and where they go, I think we can all agree that what the NWS and NOAA provide with their limited budget is pretty remarkable. Of course, we also, these data sets are subsidized by the federal government and then used in private companies like DTN or media to disseminate that information, right? Oftentimes put a nice bow on it, package the data that's maybe a little bit more user-friendly, or provide stakeholders with decision-making tools, whatever it might be. And severe weather forecasts are no different. I mean, their private companies are doing all kinds of really cool things with data that originates from NOAA, or perhaps even their own private data to get information to their stakeholders to better alert them of hazards of severe weather. And honestly, over the last 60 years, this has resulted in a reduction in the amount of people getting killed. And in fact, you can see when that trend started. It started right after the tri-state tornado in March of 1925, where we had the highest number. And that time, you have to understand how remarkable this is. The tri-state tornado of 1925 killed the largest number of agricultural farmers from any tornado ever in history. And you have to understand how remarkable that is at the time, because at the time of the 1920s, as we were entering really a period of significant depression in the Dust Bowl, farmers, anybody that was on a farm doing agriculture, was so keenly interested and tied into weather that they were really their own kind of bread and butter taught meteorologists. To have so many farmers killed that day was remarkable, and I think speaks to the just anomalous nature of that particular tornado. But look at what has happened since then. We've seen that your chances now of dying from a tornado in the United States compared to 1925 has gone down by an order of magnitude. And we know that this is never going to get to zero, because you can do everything right and still get killed, unfortunately, by a tornado. You can still take shelter, and you have these, horrible stories like we heard in May 20 of 2013 with the Moore tornado in Moore, Oklahoma. And we know that, just not everybody's going to listen or heed the warnings as well. So while it's a admirable goal to want to get to zero, we know that that's not going to happen. But we know one of the things, one of the goals of the Weather Service, right? One of their mission statements is to protect lives and property. And so we really want to get this number as low as possible. And right now, what you'll see is, if you look at tornado fatalities, they are largely disproportionately occurring in manufactured, pre-manufactured housing. This is not necessarily a warning issue. It's a communication and societal issue. And as much as we want to think we can increase lead time, it's not going to matter if somebody is still in a structure that cannot withstand EF0 winds without collapsing. This is an engineering issue. This is a societal issue. And quite frankly, when the paradigm has always been tornado warning, go to your basement. Tornado warning, go to the interior of your closet. Tornado warning, go to the lowest floor. If you are in a mobile home, you should not wait for a tornado warning. You need to be moving at the tornado watch stage. You need to get to a sturdy structure. You don't need to be waiting there in your death trap. You need to get out, whether that's a tornado shelter or uh, a school, community building, something that's not, that's built to withstand greater than EF0 winds. We need a paradigm shift in the Weather Service that gets away from this warning structure for folks in the southeastern United States and starts making actionable, decisions at the watch stage. We cannot wait anymore. We're going to continue to see these fatalities because we're not addressing the root of the problem, which is the actual structure that you're in when the tornado hits. Again, I don't want to continue to toot their horn, but I will, because their forecasts are great. I collaborate with many forecasters at the Storm Prediction Center. They are some of the sharpest minds in the business when it comes to predicting these hazards as many as 8 days in advance. And this is just an example of a severe weather outbreak forecast in the Arklatex region, where you can see that really the SPC nailed this. The day 6 outlook, day 5, day 4, 3, that transitioned to a day 1 moderate risk. And for all intents and purposes, yes, there are certainly areas of false alarms, but they certainly hit the core of where the enhanced tornado activity was. And of course, not every forecast is great, and we can cherry pick and look at good ones. But I will tell you that, if you look at their skill scores over time, they've gotten significantly better, measurably better since the 1990s. And, there's no surprise. Our models have gotten better. We understand new parameters. Low-level storm relative helicity, right, is so important to tornado formation. And so the science is learning things. The technology is certainly improving. And with that, it is my hope that, our communication to people, continues to improve, because as many of you know that work in operational forecasting, you can make the best forecast in the world, whether it's landfalling for a hurricane, the best tornado forecast in the world. I don't care what it is. If you don't take the forecast to the finish line, which is the communication piece, your forecast fails. And we're struggling with that right now across the weather enterprise, because we are not trained social scientists. I'm not. I doubt many of you are. We are weather enthusiasts. We are weather junkies. We live and breathe data and science and physics and all these fundamental things that we know and love about meteorology. We're not, most of us are not trained to think about how the general public responds to our processes, to our forecasts, to our data. And that's why you're seeing a push across the weather enterprise to integrate social science into a lot of what we do. And I think it's so important. I think it's a very, a lot of people say it's watering it down the science. It's really not. If anything, it's bringing your science to market. And we need to treat it that way. And so I'm a big advocate for making sure that our forecasts are getting to people. That's a dissemination piece. But then ultimately, once you get that forecast, that you're doing the right thing with it, that you're digesting it in the way and making actionable decisions. Really quickly here before we launch into the future, and then I'll be rounding out. But I wanted to look at, this is a research project from 2 years ago. I wanted to look at how well our flagship weather model, and for those of you who are familiar with the United States flagship weather model, this is the GFS. Many of you probably are keenly aware of the European versus GFS war that goes on in terms of skill. It's often funny, a lot of people talk about this skill as, we're verifying 500 millibar heights against one another, and yet where the forecast matters is on the ground, but we have this legacy skill verification of verifying 500 millibar heights, which I think is comical. But I wanted to just kind of take a look, like, if you're only using model data, how well could you predict a severe weather event? And at what lead time would that skill be no better than a climatological forecast? So we had this previous discussion before we started talking about the utility of AccuWeather 45-day forecast. Well, I wanted to just look at the utility of the GFS. And if you were trying to make a daily forecast of severe weather and you're only gonna forecast based on what the model says, how skillful would you be? That's really how this works. So we're all familiar with the outlook process. So here's an example, right? SPC forecaster makes an outlook. This is for the Rochelle Fairdale tornado of 2015. This obviously happened in my backyard, so I wanted to use this event. Okay, here's the forecast. Here's what actually happened. So the red dots are tornado reports. So I'm going to flip back and forth there. You can see. How would you grade that forecast? I'm gonna let you post in the chat. How would you grade that? So let's say A through F, or 1 through 10, 10 being good, 1 being bad. How would you grade that forecast? I'm going to see if I can open up the chat here. Kevin says A. We got a B. We'll see. We're going to find out who the difficult graders are in the group here. Yeah, B. Okay. Here's my point. It's subjective, right? Was the greatest tornado risk in north central Illinois and a coordinate with where the EF4 Fairdale tornado happened? You bet. That's a good forecast. But what about all the false alarm area in Indiana? What about the false alarm area in Arkansas? Should we expect forecasters to be able to draw a small 2%, 5% contour for isolated tornado events? The issue becomes, folks, is that this is a very subjective process and there's a better way to do it. And so I developed I utilized a previous method and adapted it. I shouldn't say I developed it, because nobody in science, as you guys are probably aware, really creates anything new. We stand on the shoulders of people that come before us. But this is a method to smooth data. It's basically a kernel density estimate. So you basically have something like this. Let's say we have some reports that happen in the Central Plains. You then you fit them to a grid. So you assign all of the reports to a structured grid, and then you go over that grid and you kind of smooth it, okay, with a Gaussian kernel. And ultimately what you can do is create what a perfect forecast would have looked like had the forecaster actually knew what was going to happen. And this paper is actually not in review anymore. It's been accepted to BAMS. It'll be out, if you get the Bulletin of the American Meteorological Society, it will be out in the February issue. So you can read about this more. But the process here, is just to generate what a perfect forecast might have looked like from the SPC, so that we can actually objectively grade how well these forecasts are. So to do that, I'm going to basically take what I'm going to call the practically perfect fields. So this is the outcome, right? This is the target. This is, if you were an SPC forecaster on this particular day, you should have had a 5% out in Kansas, and you should have had a broad 2% across the Great Plains. We're going to use this as our target, right? This is what we want the model to predict. We want the model to predict practically perfect. To predict practically perfect, we're going to use the GFS ensemble, all 21 members of the GFS ensemble. So a lot of you probably look at the GFS, but there is an ensemble version of the GFS, which has lots of different perturbations to the initial conditions and allows us to assess uncertainty at lead times, which is exactly what we want to do in this particular case. And we are going to use the supercell composite parameter, which is a composite parameter that involves CAPE, deep layer shear, 0 to 3 kilometers storm relative helicity, to try to predict these practically perfect fields. We're going to do this for lots of forecasts. I'll show you how many in just a second here, but we're going to look at it through the entire 384-hour forecast. When I did this study, I didn't have access to the new GFS yet. We're doing some new studies that are using the new GFS ensemble to see if there's any greater skill. But we're looking at this 6-hourly output out to 384, and we're going to use the supercell composite to actually predict this practically perfect. So here's the equation for the supercell composite parameter. If you're a severe weather junkie in this call tonight, you know exactly what the SCP is. I don't have to tell you, but it's basically go back to this ingredients-based approach. We're trying to look for ingredients in the model that would be conducive to producing tornadoes and hail. And it makes a lot of sense, right? If you have a rotating thunderstorm, it's probably more likely to produce significant severe weather. So to do this, we take every forecast. We did this for every forecast from March 1st to May 31st in 2016 and 2017. So we had 92 forecasts a year for 2 years. We had 21 members per forecast cycle. So we evaluated just under 4,000 forecasts. And we did this for both hail and tornado, just to see if the skill was any different between predicting the practically perfect hail field and the practically perfect tornado field. So here's a visual example of how this method works. We know the outcome, right? On a particular day, we know the outcome. So that would be the practically perfect. We look at a specific practically perfect threshold and say that is going to be our target. And so, for example, in this case, I'm going to make it 5%. So we want to forecast the 5% target. So that would be this area. Then we go to the GFS and we say, okay, we know the outcome. What is the predicted supercell composite for that particular day that is greater than a certain threshold? So for example, I'm showing you here, this is where the mean of all supercell composite parameter members is greater than 2. Okay, so again, maybe we took all the members, we averaged them, and this is where the threshold that we choose is 2. And then we can actually score this forecast because we have a representation of the outcome, right? We have a predictor and a predicand. And that's exactly what we did, right? The areas in purple are where we hit the forecast. Great. The areas in blue are where we had false alarm, right? This is where the model predicted something was going to happen, but it didn't. In the red, that would be an area of miss. That's where reports happened or practically perfect was greater than the threshold, but we didn't have any forecast there. And the rest of the country was what we consider a correct null. I'm knowing what you're thinking. Yeah, there's a lot of correct null. When you deal with extreme weather events, your correct nulls are always going to be much larger than your hits, your misses, or your false alarms. And so you must look at verification metrics that do not account for correct nulls. And one of them that does not is the critical success index in the Breyer skill score. You do not look at correct nulls because, you know, I don't want to get credit for not forecasting a tornado on this day in Washington, right? I don't want to get credit for forecasting that nothing is going to happen in Maine. So we throw out all the correct nulls and we only look at the hits, misses, and false alarms, as those are really the most important aspects of the 2x2 forecast contingency table. So I'm going to speed through these results here, but this is what our research found. If you're forecasting, and the only panel here, folks, that is important is panel C in the lower left, looking at the Breyer skill score. The Breyer skill score is how good are you relative, how perfect is your forecast relative to climatology? If your forecast is negative or 0, climatology is better. If your forecast is 1, it's a completely perfect forecast. So these are the average Breyer skill scores for all nearly 4,000 of those forecasts for March, April, and May 2016 and 2017. And what you see very clearly is there's this diminishment in skill that we know exists through chaos theory. Skill for forecasting hail events is slightly greater than tornadoes because of our larger sample size, most likely. But there is no skill beyond day 9 for daily tornado events. And there is no skill beyond roughly day 11 for hail events if you're strictly looking at dynamical output from the GFS ensemble. I don't really honestly expect these results to change much, maybe by a day or so, if you're looking at different ensemble systems, say the European ensemble or time-lagged ensembles of the CFS or whatever you want it to look at. It's just, right, it's the inherent difficult nature, number one, of predicting these events, but the fact that the skill does diminish so rapidly due to errors in the initial conditions. I said all of that to now say that there can be skill beyond 1 week. Well, I shouldn't say 1 week, right? 1 week would be here. There is skill beyond the early parts of week 2. It's just not the type of skill that we're used to. It's not daily forecast for temperature. It's not daily forecast for severe weather. There is skill when you relax the time and space constraints of your forecast target. So instead of looking at tornadoes in Minnesota, we're going to look at tornadoes in the Midwest. Instead of looking at tornadoes on a day, we're going to look at tornadoes over the course of a week. When you begin to relax the time and space constraints of the forecast target, your skill inherently goes up because you're reducing the dimensionality of the problem. And so what I'm really passionate about right now, for those of you who know me and probably talked about this at the Severe Storms Doppler Radar Conference when I saw many of you in person, is this growing, budding area of subseasonal forecasts, which is really a new horizon. And I think it's the most challenging horizon because you don't have dynamical prediction, which are weather forecasts, and you don't have statistical forecasts, which are seasonal. You are in this hot potato purgatory of where I just demonstrated, right, that dynamical skill drops off very quickly after 1 week and approaches zero. So how then do we get skill? And it turns out that there is a bridge between this deterministic weather forecasting and the seasonal forecasts that are put out by folks like CPC and the private sector, right? Energy consumption, et cetera, et cetera. And this is where I think a hotbed of research is focused on right now. What is this bridge? How do we forecast? In my perspective, I think this is an area that is going to require improvement in our dynamical models, but also harnessing what skill is left in week 2 with statistical models, machine learning, understanding of the sources of variability like the Madden-Julian oscillation, which I'm going to talk about here tonight. And then that's going to be our bridge to making more skillful forecasts in the 2-week to say 2-month time frame. I want to also be clear that subseasonal forecasts are not always skillful. And if I've learned anything in my relatively limited career of working on this, it's that these forecasts are forecasts of opportunity. They are not always there, but when they are there, where they do present themselves, you can easily harness skill into week 4 and even week 5 if you're watching and diagnosing the atmosphere in a very keen manner. I think machine learning is going to really help us with this, but here's just a plethora of papers that have been published on the leading modes of variability and how they influence severe weather. I've published a lot on the GWO. You might have heard about that. Angular momentum, which is basically GWO. The Madden-Julian oscillation. You've probably heard a lot about El Nino, La Nina, right? And ENSO. We were just talking previously on the call of how ENSO influences Midwest winters. It's not an easy problem. And if you try to reduce it to this parameter does this in this location all the time, you will find out very quickly that you will fail. Thinking about the atmosphere as, there's only one parameter and it's a silver bullet is not the way to do this. The atmosphere, all of these teleconnections, I like to think of them as an orchestra. They're all playing in concert together. Sometimes some are singing, playing louder, and they trump the pattern, if you will. And sometimes they're not important. And we're still learning a lot. I have a National Science Foundation grant right now that's really dedicated just to this problem of trying to better our understanding. But I want to do a little education tonight. I want to do focus very quickly on the Madden-Julian oscillation. I don't know, the familiarity with this particular oscillation of many in the group, but the MJO was actually identified in the early 1970s by Madden and Julian, and it's roughly a 40 to 60 day cycle of convection in the equatorial Indian Ocean and Western Pacific. And the cycle goes something like this. Convection develops across, you might have a stalled out easterly wave that then initiates convection over the warm waters of the Indian Ocean. You get significant latent heating occurring in the vicinity in the mid levels with this convection, and that basically momentum, right, is transported to the troposphere. And as it goes poleward in both hemispheres, it has to conserve its angular momentum because it's getting closer and closer to the Earth's axis of rotation, right? It's getting closer to the poles. So it basically acquires a zonal velocity when it does that. This convection propagates against the easterly flow that you see in the surface. So think of the trade wind easterlies, right, that we see in the tropics. This convection propagates against that. The upper level winds in the lower stratosphere and upper troposphere actually propagate the convection against the surface trade winds that you generally see in the tropics. And so there have been, and again, this has been studied, pretty rigorously over the last 30, 40 years. But we generally say that the convection, the MJO phase is in one of 8 places, right? You can see this particular example would be like phase 2.5, right? Convection is moving from phase 2 to phase 3. And so as convection starts in the Indian Ocean, propagates across the maritime continent, and eventually gets into the Western Pacific, it will go through this 1 through 8 cycle. Okay, 1 through 8 cycle. And so given that it's on the order of 40 to 60 days, that's exactly right the time window that, if you go back to understanding subseasonal forecasts, this is really what we find through some very basic theoretical modeling work, is that if you want to really get a good handle on subseasonal variability, of course, there can be other things going on, ENSO and yada, yada. But if you want to get a good handle on subseasonal variability, you ought to be looking at this tropical forcing associated with the MJO. This is so true for the United States because everything that happens right across the Western Pacific is really just a day or two upstream of us in terms of Rossby wave propagation in the mid-latitude westerlies. So this is science and research has really identified this MJO as one of the dominant modes of northern hemisphere climate variability, and it's something that I've been looking at quite often. So how do you track the MJO? If you want to do this on your own, it's actually fairly straightforward. You can go to the CPC, the Climate Prediction Center website, and you will look at these, what we call Wheeler and Hendon diagrams, these phase space diagrams. And so you can see in this particular image, when I captured this in 2012, the convection was in phase 6, and it was fairly strong. The distance away from the origin, you can kind of think of this as a polar coordinate plot, even though it's Cartesian. You can think of it as polar. As you get further away from the origin, the signal of the MJO is stronger. And so these are basically the leading modes of variability, yada, yada. You don't need to know that. But you can, we have forecasts for the MJO, but you can see what generally happens. You can look at, I just mentioned, right? MJO goes from phase 1 through 8. Look at how this goes on this phase space diagram, right? On a phase space diagram, the MJO will rotate in a counterclockwise manner. So you can see how it went from phase 8 to 1, back to the Indian Ocean, right across the Indian Ocean, then across the maritime continent, phases 4 and 5. And then at the time this plot was made, it was in phase 6 and was forecasted to go through phase 7 and significantly weaken by the end of the forecast. It's nice because this is really predictable, right? We can develop very simple linear inverse models to model the MJO from a statistical perspective. And there are a lot of products out there that, forecast the MJO 30, 40, 50 days in advance, because we know it's a very consistent forcing mechanism in terms of its seesaw variability and what it provides to us to capture. You can mathematically do this with angular momentum. I'm not going to get into that tonight for purposes of brevity, but here's kind of how this process works. As a severe storms forecaster, or really any extreme weather, what I would be looking for is a significant amount of convection developing in the equatorial Indian Ocean. If I see that, I'm going to keenly begin to watch the charts that I have in-house, and I have some of them publicly available if you're interested. I'd be looking a lot for a positive mountain torque and frictional torque signal, especially in places like the Tibetan Plateau, where I know flow is going to be going across topography induced by this increased convection, and probably looking for a negative Pacific North America pattern to be setting up across portions of the Northern Hemisphere. Then after that occurs, about a week later, if you're looking at severe weather in the United States, it's actually about 8 times less likely that you'll have any significant weather during this convective blowup in the Indian Ocean and the subsequent transfer of that angular momentum into the Northern Hemisphere budget. About 2 weeks later, average F2s are about 3 times less likely. But the pattern now is going to go under a major shift. We've just now probably extended the jet across the Pacific Ocean, and the handwriting is on the wall for a large retrogression of the Northern Hemisphere pattern and troughing to begin to set up in the Western United States. And so then about, again, the timing of this, I'm showing you a very textbook example, but the timing differs. But I sort of got this idea from watching, I was actually watching the World Series, and I'm sure many of you are familiar with the heat zones, right? Where do you not want to throw this batter? Don't throw them alone inside changeup because they're going to crush it. I wanted to do that with the MJO and the GWO. I wanted to basically plot heat zones of where tornadoes were most likely. And it just so happens that in this lower phase space, lower left, phases 1 and 2 of the MJO coming out of a phase 8 is really where we see the most significant tornado activity across the Great Plains. And if you look at the pattern at this time, it's generally a big southwestern United States trough, right, with strong flow over the plains, strong moisture advection from the Gulf in that upper level southwesterly regime that's creating favorable environments for tornadoes. Really quickly, I want to show you how we put this to work in 2019. So this is late May, flashback to a really active period. May is usually fairly active, but this particular May had 757 tornado warnings during this 2-week stretch from May 17th to May 29th, had 757 warnings, 374 prelim tornadoes. That's about 3 times the average May value for all of May. Luckily, we only had 7 fatalities, and it was the second highest count for any May since 2003. The rest of the season was actually fairly a dud in May for significant tornado activity, but it was really well forecasted. In fact, we wrote a paper on this that looked at a successful 4-week forecast for understanding the probability that severe weather was going to be a very favorable regime for severe weather was going to develop over the central United States because of an MJO event. And I want to show you how we knew this. 4 weeks prior to that 2-week mayhem in late May, there was a significant increase in convection in the equatorial Indian Ocean as outlined by this area of green. These are outgoing long wave radiation anomalies, and I have them contoured here at about I believe the 40 watt per meter squared, I want to say contour or something like that. It's kind of where the significant convection, right? Wherever you have this black outline contour is where there's significant convection occurring. So the MJO at that time, if you look at it in phase space, remember our numbers here, 8, 1, 2, 3, 4, 5, right? Back to 1, 2, 3, 4, 5, 6, 7, 8. You're basically, once you see this signal, the MJO goes from being dead in what we call the wheel of death with nothing happening here to all of a sudden flare up in phases 1 and 2. So in late May, really the last week in May, we saw this huge increase in tropical convective activity and an active MJO beginning to occur, right? Phases 2 and 3, which is right there in the MJO region. 3 weeks later, that convection had propagated all the way to the center of the maritime continent and sometimes does this, will begin to split off into both northern and southern hemispheres. This happens due to Rossby packet breaking. There's a lot of dynamics going on here that this is occurring, but you really now see kind of an asymmetrical convective signature that's developed over the maritime continent in both hemispheres. The MJO is progressing, right? It's propagating. And so here's what the next week, this is T-3 weeks to the event. Here's the propagation of MJO during that time frame. And I should mention the gray circles here are the number of tornado reports that are occurring in the United States. So the larger the circles, sort of the bigger the day that we had. T-2 weeks, the propagation of the convection is now almost out to the international dateline. Strong subsidence over the Indian Ocean, very classic MJO propagation here. And what you see is, again, this continued progression through phases 6 and 7 of the MJO. This is usually where, as a forecaster, you see that big jet extension and you are beginning to watch the GFS going, yep, we're now within 2 weeks. Some of the ensemble members are saying this is going to get big. And you begin to kind of watch every individual run and hanging on, right, what the dynamical models are doing. This is a really classic signal, 4 weeks prior. But here's T minus 1 week. The convection is all the way out now past the date line, still strong substance over the maritime continent, Indian Ocean. There's the progression of MJO. And usually now, where the hot zone is, right? You remember the hot zone is down here. This is where we have this is where you don't want to, if you're the atmosphere, if you want a tornado, you want to get down, at least big tornado outbreaks, you want to get down into this phase space. Really anywhere in phases 8, 1, or 2, as you're transitioning through what we call this 8, 1, 2 transition, that's where the extreme events occur. So here's the first week of the event. We spent a lot of time in phase 8. We did finally propagate through the second week. And look at all the gray circles here. This is basically day after day after day after day of at least 25 tornado reports occurring in the United States somewhere. And some of these days are really prolific outbreak days. I think I have the synoptic composites, so you can kind of see how this developed. This is T minus 3 weeks. Look at, this is the 200 millibar hectopascal average wind. So you're basically looking at jet stream level winds. Notice the jet structure coming off the East Asian continent. That's T minus 3 weeks, minus 2 weeks, minus 1 week. We see this classic North Pacific jet extension, and that usually sets up the pattern that it will then retrograde and basically what we call wave breaking. It's exactly what happened here. A beautiful jet extension, retrogression. And of course, if this is the first week of the event and this is the second week of the event, you basically have stationary southwesterly flow over the Great Plains and Midwest for a 2-week period. And of course, when that happens in May, the Gulf is wide open. You're going to get severe convective storms. So it's really no surprise from a synoptic perspective why this particularly happened. So I'll conclude here by saying that a few years ago, we started this project to just see how successful we could be at predicting severe convective storms, specifically tornadoes, at 2-week and 3-week lead times. And we've had some success. We published this in the Bulletin of the American Meteorological Society, BAMS. So if you want to read more, you can check out our BAMS article. But we've gotten a lot of attention for this, both good and bad. Some people say, well, why are you doing this? And I say, because I can, because it's fun. There's always haters, I think, in anything that you do. But what we're really trying to do is just push the envelope of the science, and really by exercising and participating in the forecast, but also the verification of your forecast, you learn a lot about how good you are as a forecaster, what tools you're missing, what you wish you had, what you need, what you would prefer for observations. And so, it's just it's kind of a labor of love project, but the verification angle is really important, because we could pull AccuWeather, right? We could pull this as a marketing stunt where we continue to issue these forecasts and don't verify them, but we wouldn't really be learning anything from that. And that's why we do post the verification along with a lot of what we do. So I will wrap up by saying, once again, coming back to this theme, that we can create the best forecast in the world, and we're still going to have tragic events, whether it's Moore, whether it's Joplin, whether it's Fairdale. It doesn't matter. These events are going to continue to happen, and I would argue are going to happen at a much higher frequency than they ever have in any point in history, because of our developed footprint. And this goes to some research that my colleague at Northern Illinois, Dr. Walker Ashley, has beat this drum since the early 2000s, talking about the role and importance of changing land use, land cover in tornado disasters. And in many ways, this is a very, very simple thing, right? If you close your eyes and throw darts, and the only thing that's changing is the dartboard is getting larger, you're eventually going to hit the dartboard, right? You're going to hit the dartboard more. That says nothing about the intensity of the tornado or the frequency of tornadoes changing due to climate change. This is strictly just changing the urban built environment. And we've seen this. We're going to continue to see this as we go forward. More of these tornado disasters, just because we really have more assets, more targets on the dartboard. So I think currently I'm really optimistic about subseasonal forecasts. I think our forecasts are getting better. I'm hopeful that we haven't hit a critical point, but I would argue that for those of us who do a lot of severe storms forecasting, I think our models have hit a critical point. We made a huge leap when we went from convective parameterization to convective allowing. When we switched to CAMs and we got down to 3 kilometer, 4 kilometer horizontal grid spacing, that changed severe weather forecasting. I do not believe with the current observation networks that we have, we are going to make another one of those significant leap forwards, even if our computing continues to get better, which we know it will. We can run thousands of ensembles, but they will be under dispersed if we don't have good observations. You don't have to be a severe storms forecaster to understand that if you put garbage into any model, you're going to get a garbage forecast out. And so our forecasts are still going to only be as good as our observations that are going in. And I'm, theoretically, my brain thinking every day, are we going to be able to do war-on forecasts? Do we have the observations necessary to carry out these simulations that are probably needed to be able to push that paradigm and make it reality? And even if we do have great forecasts, we're still going to have events and we're still going to have people die unless we address the issues of exposure and vulnerability. I think many of you on this call understand that. And I've talked to many of you on this call about exposure and vulnerability and how important of a role it plays in all hazards, not just severe convective storms. I'm a little bit over time here, so I don't want to take up all of your evening and talk a little bit about the future. I have done some work on future climate simulations of severe storms and how we expect those to change. I'll basically leave it by saying the simulations that we've performed to this date regarding climate change impacts, not saying anything about land use, land cover, the climate change impacts are actually fairly clear. We think we're going to have more severe convective storms in the aggregate. We can't really say much about tornadoes versus hail versus damaging wind right now. We think the mean is going to increase, but we also think the variability is going to increase. In fact, you can see this with this chart here. This is basically the accumulated number of severe weather reports from our climate models. You see some of the lowest years in the future, and you also see some of the highest. So you see sort of the spreading of the standard deviation, which really I think lends itself to this idea of the changing variability of having some seasons that are just super active, early on stay active, and then other seasons that are just kind of northwest flow, if you will, into the plains and cold fronts crashing into the Gulf and just not allowing a favorable regime to set up for a significant amount of time. Of course, you're always going to have mesoscale events and things like this, but even from a subseasonal perspective, those are not the ones we're trying to forecast for. We will have always very little skill in June, July, and August when the pattern is predominantly driven by mesoscale circulations. Our target of opportunity comes in April, in March, and early May, when the dynamics are really driving the global circulation at a synoptic scale and planetary scale, not necessarily at a mesoscale. And so, that's something that we know is going to be a challenge. We know this as a weather enterprise. Our forecast skill tanks in the boreal, the northern hemisphere warm season. I mean, it is what it is. The convection and outflow boundaries, influence the next day's forecast, and it becomes really, really challenging. So, I think with that, I'm going to pause, and I've talked enough, and I like to entertain questions. I'd like to entertain conversation.